Hello, scholars. Today we're learning about a simple linear regression, which is a statistical method or a model to determine if there's a relationship, a predictive relationship between a dependent variable and an independent variable using a straight line. It can also help identify trends. It can show you the strength of a relationship, weak, moderate, or strong, and the direction, positive or negative. Um, and it can tell us how much of the variance of a dependent variable is explained by the independent variable, or how much of the variance of the outcome is influenced by the predictors. That's an easier way to remember it, isn't it? So how much does the outcome change because of the predictors we're testing? So an easy example to understand a simple linear regression. Does the average hourly temperature predict the number of ice cream cones sold each hour? If it does, just by knowing the average hourly temperature, I can know how many ice cream cones I would expect to sell and how much for each degree of change that affects the number of ice cream cones sold, going up or down. Okay, so as with everything, all statistics, inferential statistics, have assumptions about data and assumptions for testing. The data assumptions of a simple linear regression are one dependent variable or outcome variable that is measured at the continuous level, ratio, or interval, and one independent variable that is measured at the continuous level, ratio, or interval. Now, there is an exception to that rule, which will be discussed in a separate video. You can use in regressions categorical or grouping variables using something called dummy coding, and I will discuss that in a separate video. It's not discussed here. It's just possible. Okay, so the independent variable is also known as the predictor variable, the explanatory variable, or the regressor variable. The dependent variable is also known as the outcome, the target, or the criterion variable. So the testing assumptions for a simple linear regression include the assumption of linearity, that the relationships between the two is linear, and we look at a scatter plot for that. Number 2 is independence, also known as no autocorrelation. And we use a Durbin-Watson test for that. So the observations should be independent of one another and not correlated. Homoscedasticity. This is when the residuals have a constant variance across all levels. Okay? And we inspect a scatter plot of standardized residuals. I will have a separate video explaining what residuals are. And finally, we want normality of the residuals. Okay? So the residuals should be approximately normally distributed for your simple linear regression. And we look at a histogram of the residuals. You can also look at a QQ plot of the residuals. Okay. Now, when these assumptions are violated, I select a different test. Please note that there is something called data transformations. And I don't like them because they can change, depending on what you're doing, they can change the value of each data point. Sometimes when these assumptions are violated, you can use a logarithm or square roots, and you can impute half or all of the mean score into each data point, and then they can pass these assumptions and you test that. I personally feel that these are unethical and you should simply switch to a more appropriate test most of the time. Okay, so while you're finishing class with me, you will not be transforming data, but you should be aware of it in case your dissertation chair or some other professor requires it. All right, so today our research question is, does a person's job satisfaction predict their organizational commitment? So that's beyond a relationship, right? Is there a relationship between job satisfaction and organizational commitment? We're asking, for every change in job satisfaction, what is the change in organizational commitment is part of what we're asking here. So there's my null hypothesis, which is what we're testing. A person's job satisfaction does not predict their organizational commitment. So we can see that both of the independent and the dependent variables are continuous. And again, I will provide a video about dummy coding. Now, we will check the assumption of linearity first. So to do that, you can open your JASP file. You can go to descriptives. From the drop-down, you pick descriptive statistics, and we can order our scatter plot under customizable plots, right? I don't need density on the sides of any of these things, but I do want my regression line. So it'll give me my scatter plot. And in the meantime, you should always order your descriptive statistics, skewness and kurtosis, and mean, median, and mode, that sort of thing. Notice that I do not order a Shapiro-Wilk test. I do not order a Shapiro-Wilk test because the assumptions for that test are already violated. Okay, the residuals are not independent of one another. So I'm not going to do a Shapiro-Wilk. I'm simply going to inspect my scatter plot. And I'm still waiting for it to come up. Here it is. Okay, now let's look at this scatter plot. I believe I have a bigger picture of it right here. It looks like it's starting to form a line to me. So I'd say the assumption of linearity is met. If your assumption is violated for the paper from me, I want you to state so and proceed with your test. However, in real life, you would suggest a test change or you'd transform your data. In this case, I would either do, if this was violated, I would either do a polynomial regression or a nonlinear regression. I'd probably pick polynomial. All right, the next assumption is for independence of observations, also called no autocorrelation. Okay, and I am going to order that from the regression itself. That is called a Durbin-Watson test. You can find it under statistics and you just check the box. And it's going to give you this model summary output up here, which includes the Durbin-Watson test right here. Okay, now notice my p-value is p equals 0.949 and my statistic is 2.016. Why does that matter? Well, there's two ways I can check that test result. Okay, I can look at the Durbin-Watson statistic itself. Less than 2 or about 2, there's no autocorrelation assumption met. Less than 2 or positive than 2, if it's pretty far away, then we might have positive or negative autocorrelation. But JASP tests the null hypothesis that there is no autocorrelation in the residuals, hence the p-value, right? So I can go back and I can look at this, and my p-value is fail to reject the null. P is greater than 0.05, right? Remember that. We use 0.05 in social sciences for alpha. My p-value is higher than that. We fail to reject the null. The null states that there's no autocorrelation, so my assumption is met. If your p-value is below that, you reject the null, and then the assumption is violated. Okay? Now, when you look at my model here, for this one, I'm only interested in M0. I can look at both of them. I could look at this one too, but you can see that both have no autocorrelation involved. And I show you how to report it in APA right here. Durbin-Watson equals 2.014, comma, P equals 0.949, meaning that the assumption is met. Now, if the assumption was violated, you could transform your data, which I won't do, it's unethical, or you can change test. In this case, I'd use a generalized least squares test. Okay. Now, the next test is the assumption of homoscedasticity and normality of the residuals. So these are two more assumptions. So homoscedasticity of the residuals test, I'm going to order it from the residual plots underneath my regression. And to order all of this, I go to regression, linear regression, and I have to remember, I have to move the variables I'm testing into their appropriate places. And now I'm going to go to plots, and I'm going to collect residuals versus predicted. And I'm going to select residuals histogram for the assumption after that, right? Now, here's my scatter plot for homoscedasticity. I'm having trouble saying that word. We want everything to just sort of look scattered. We don't really want to see a pattern. If I'm starting to see patterns like cones or fan-shaped, something other than maybe a bit of a line is okay. But if I see cones or fan shapes, the assumption's violated. Okay? So if I had to recommend a different test, I might use a weighted least squares test if this assumption were violated, or a robust standard errors regression, or just a robust regression. I would probably use weighted least squares or a robust regression. Now last, we'll look at that histogram of the residuals for normality. You can also use a QQ plot, which can be ordered right here, right there. It's right underneath that. So we can add a QQ plot. Now here is my histogram of the residuals. I'd call that approximately normal. Here's my QQ plot. You can look at both if you want to confirm, but I would say mine are approximately normal. So scholars, once your assumptions are all met and you've checked them all, we can proceed with our simple linear regression, which you have already ordered while you did all of that. Okay, so the first thing we typically predict is the ANOVA table. And the reason we predict that is it tells us if our model the simple regression was a good fit for our data. Okay, and you can see I get an F statistic like I do for any ANOVA, and I get a p-value. Okay, and this M1 means that job satisfaction is included as a predictor in my model. All right, so we have a significance. P is less than 0.05. This means that according to the ANOVA table, the simple linear regression was a good fit for our model. Okay. Now, the next thing that we want to interpret are the coefficients. So for a simple linear regression, we discuss R and we discuss R squared right here. Now remember, this right here, the first model M0, just gives us the baseline and the intercept, which is the average of the dependent variable. End of story. So it means without anything, without adding a predictor, we're starting off at 0. Okay, but M1, this adds our predictor variable, and in this case, that's job satisfaction to the dependent variable of organizational commitment. So our R value is almost 56, 0.56, 0.558, we rounded up, and R squared is R squared literally, which is 0.31 if we round it. So this is a moderate effect size. Okay. So we can see the effect size. These are just suggested. Okay. So we would say that this is a moderate effect size or a moderate relationship. Now, the R squared pertains to the variability, how much of organizational commitment my predictor variable explains job satisfaction scores. So 31% of, 31% of organizational commitment, the dependent variable, is explained by the predictor variable of job satisfaction. So, unlike a correlation, these numbers do not provide the direction of the relationship, only the strength. Now I'm going to get the rest of it from my coefficients table. Okay, so I'll interpret both the model MO, which only provides the intercept. It's the baseline without adding the predictor, so it's just the average of organizational commitment, basically. I show you how to write it right here by color coding it. Here's the intercept, the standard error, and then we provide our T statistic. Okay. Now, for the full model, which in our case is M1, I'll provide the intercept, the standard error, and the T statistic again. But I'm getting it from this line. Okay. And then finally, I'll report job satisfaction, the intercept, which is 0.9, the standard error, the standardized coefficient of 0.56, and my T statistic. So what does that mean? So look at that right here. Okay. So it was significant. And basically what this means is 0.90, right? See where I got this from? The unstandardized coefficient of job satisfaction. For every 1 unit increase in job satisfaction, the outcome of organizational commitment increased by 0.9 units. I got that right here. So if all else was constant, that's what it means. So after this is all said and done, I reject the null hypothesis in favor of the alternative. Job satisfaction explained 31% of organizational commitment, which means for each 1 unit of increase in job satisfaction, the predicted outcome of organizational commitment also increased by 0.90 units. And again, I got that right here. Okay, I will do separate videos explaining what residuals are and a separate video explaining what dummy coding is. Thank you very much.